Hey guys, I hope your exams have been going pretty well, and I hope that biology wasn't too much of a pain in the neck. You guys seem to really like me doing the biology paper, so I'm definitely going to be continuing with the chemistry and then the physics paper. So this chemistry one's going to come out hopefully just before the chemistry exam, otherwise it's a bit useless. But I'm just doing the most recent past paper. Again, the link is in the description for the paper, but hopefully I'll kind of go through, obviously give you the mark scheme answers, but also provide some context, some exam technique, and obviously some more explanation just to kind of really solidify it in your mind. So for the first question, we have a fairly simple experiment that they're running, and what they're trying to investigate is the reaction between magnesium and hydrochloric acid. So they're kind of looking at rates of reaction, and this is the method that they have. So this is the kind of setup, the apparatus that they have, and this is the method. So they put 50 centimeters cubed of hydrochloric acid into this conical flask. They add the magnesium, and as they react, of course, it's going to produce a gas. And what that's going to do is fill up the gas syringe, and they'll be able to read off the volume of gas produced. And what they're going to do is every 20 seconds for 2 minutes, they're going to kind of note down what the volume is. So 0 seconds, there'll be 0 gas produced. Then 20 seconds, maybe there's 10 centimeters cubed, and so on. And then what they're going to do is do the same thing with higher concentrations of hydrochloric acid and see what happens. So does the rate of reaction increase, decrease, does it stay the same? Who knows? Okay. Now, this tends to be one of the first questions in these kinds of experiment questions, is the independent versus the control variable. Now, here's the way I think of it. The independent variable is the one you change. It's the one that you're controlling, okay? This is the one that you change. The dependent variable is the one that changes in response. So in this case, I know it's not asking for the dependent variable, but I figured I'd go through it. The independent variable is the concentration of hydrochloric acid. Because look here, it repeats with higher concentration. So that's what I'm changing if I'm doing this experiment. So that is just the concentration of hydrochloric acid. Again, don't use any kind of contractions or anything. So I have just used one myself. But concentration of hydrochloric acid is what you're going to look at. Now, what is the dependent variable? What is going to change in response to the hydrochloric acid changing, the concentration changing? Well, it's just going to be the volume of gas produced in a given amount of time, okay? So you could just say volume of gas produced. Now, what about the control variable? Well, here's what you need to think of. You need to think of anything else that can affect this. Now, I'm thinking of rate of reaction, aren't I? Because I'm seeing how quickly a certain amount of gas is going to be produced, which is why we do it every 20 seconds. So what else affects rate of reaction? Well, the big one is temperature. So we want to keep the temperature the same, because that could affect my experiment. What else could affect it? Well, what else affects rate of reaction? The surface area of the magnesium. So you need the same size and thickness strips, okay? And you have to make sure there's no indentations or anything. And you need to make sure it's a whole strip as well. All of those things would affect surface area. So you just want to say surface area of magnesium. So length as well, I included in there. The volume, so the actual amount of magnesium you put in. And those are kind of the main ones you're thinking of. Just think of rate of reaction when it comes to that. For the second part, we have to actually plot this data that they give us and draw a line of best fit. And just as a preface, just keep in mind that my ruler is not perfect. It goes up by individual. I mean, look how much it changes by just a tiny amount, right? Like, it's a big jump. So my line of best fit may not be absolutely perfect, but again, hopefully I'll explain it to you in a good way. And all you need to do is plot these points. It's a little bit of maths in this case. So 0, 0 has been plotted for us. And then 20, 48. So here, make sure you're plotting them in the correct area. So 20 and then 48, make sure you know what these go up in. A lot of the time, students make mistakes on this. So it goes from 40 to 60, and it's in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 squares. So it's not going up in ones, it's going up in twos. So I need to go up to 48. So that's 42, 44, 46, 48, right here. Okay, so just make sure you know what they're actually going up in, what the axes are going up in. Even the x-axis are going up in twos, if you notice. 40 and 72, so 40, 72, so that's going to be, it's going to be 3 before here, but yeah, 62, 4, 6, 8, 70, 72, right here. Then you have 60 and 90, so 60 and then 90 is right in between. Then you have 80 and 97, So 80, 97, so 92, 94, 96, 97's right in between these two. Perfect. And then we have 198 and 120 and 98 as well. So they're basically going to be on the same level. Now it says line of best fit. So you might think, well, okay, I need to get my ruler and try and like get all these stuff. No, right? Not in this case. In this case, we're not doing a straight line of best fit. The line of best fit is actually going to be a curve, okay? And this is really important because a lot of the times in science, people get confused between science and maths. In maths, your line of best fit is always going to be a straight line, 100% of the time, at least for GCSE maths. In science, you can have a curve of best fit. It's completely legit. But it has to go through the first point 0, 0. So here's what I would roughly draw. Again, it doesn't need to be a work of art, but just a smooth curve. Don't take your pen off the page. And it just needs to go through all of the points, but not like a connect the dot, okay? Just something like that. Again, a bit less shaky than mine, obviously, but again, graphics tablet, not exactly the best way to do this. Okay, so that would be roughly what your thing should look like. And the key points here is that you've plotted them all correctly. That gives you 2 marks. The third mark is for a line of best fit. And remember, it can be a curve, just going through the points. That it basically just needs to follow the general shape of the graph, okay, general shape of the points. Now, the important thing with this question is to keep in mind that this is just for the first experiment with a low concentration. So this is, if we go back up here, they've done this just once, okay? So they've done steps 1 to 5. They haven't changed the concentrations. So remember, this graph here, it just shows one kind of attempt at this. So this isn't actually comparing the concentrations. So what they did is they put the magnesium in the acid, and then it started producing gas really quickly. And as you can see, it slows down, doesn't it? The amount of gas produced decreases over time. Well, it doesn't decrease, but the increase in amount has decreased, right? The other way to think of this is a gradient. It gets less and less steep. So less gas is being produced per second as we go along, isn't it? Okay. This is important because in this question it says, how does the rate of the reaction change with time? Now, the rate of the reaction is just how quickly the gas is being produced. Now, if this is getting less and less steep, let's have a look. In the first 20 seconds, it goes up to 48. In the next 20 seconds, it only goes up by about another 20. But then as it goes along, can you see it's increasing by a less and less amount? And in fact, at the end, that it doesn't produce any more gas at all. So the rate decreases. Now, if you're a bit more mathematically minded, the gradient of this curve gives us the rate of reaction, which in this case, the gradient is decreasing, so the rate of reaction is decreasing. Now, it says here, the student repeats the same experiment using a hydrochloric acid with a higher concentration. Which statement is correct? The activation energy for the reaction is higher. The magnesium reacts more quickly. The reaction finishes at the same time. The total volume of gas collected was smaller. So all we need to do is think of this individually, okay? So the activation energy, well, the activation energy can only be changed when there's a catalyst involved. That's the only thing that changes activation energy as far as you're concerned. So it's definitely not this one. And it definitely wouldn't be higher. The magnesium reacted more quickly. Well, there's more hydrochloric acid particles, so I could see that working. So this one looks probably right. The reaction finishes at the same time. Well, if the magnesium reacts more quickly or slowly, then it won't be at the same time. And then the total volume of gas collected was smaller. Well, this shouldn't be the case, because remember, the gas produced is just going to be equal to the masses or the mass of the magnesium, right? Because all of it's going to react. So in other words, it's this one. A higher concentration increases rate of reaction. Remember your kind of principles of rate of reaction. If you increase temperature, if you increase concentration, these things increase the rate of reaction, which means the reaction happens faster. It's like you're running a race, right? Increasing the rate that you run at means that it takes less time for you to complete the race, okay? And here is one of the many explanations that you need for increasing or changing the rate of reaction, okay? And I'm going to go through all of them, okay? But this one is just asking for temperature. And basically, they're all 3, maybe 4 mark explanations, okay? Very quick, very short. And a lot of it is kind of logical. So, we're talking about the particle model here. Now, for a successful reaction to happen, we need an atom or a molecule of each thing that we're reacting to collide. But not just collide, they need to hit with enough energy that they actually react. Because keep in mind, there's an activation energy. So if they kind of just bump each other, nothing's going to happen. But if they smash into each other, then we have a reaction. So keeping that in mind, we can actually explain all of these different rates of reaction kind of factors. So concentration and also surface area as well. Okay, we can explain all of them at the same time. But with temperature, let's think about it. Temperature affects the rate of reaction. Explain how increasing the temperature affects the rate of reaction. Well, first of all, we should just say if the rate increases or decreases. That's the first thing you should say. And of course, it's going to increase. Now, if that doesn't make sense just yet, give me 1 minute to explain it to you. Okay? So the rate increases. That's 1 mark. Okay? Now, why does it increase? Well, imagine you have a gas, right? And they're moving quite slowly, right? The chance of them hitting is kind of low. And when they do, they're probably not going to react because they're just bumping each other. But now imagine if they're moving really quickly, right? It's more likely they're going to hit each other. And it's more likely that they're going to hit each other with enough force to actually undergo a reaction. So now we just need to change that into words. The way I like to think of it is imagine if you and your friends are all in a big dark room and you're just walking in random directions, you can't see where you're going. What are the odds of you hitting each other if you're just kind of walking? Not that high. Now imagine if you're sprinting. All of you have to sprint. You guys are going to hit each other pretty frequently, right? So that's kind of what's happening with particles. They move randomly. They can't see where they're going, but they have to hit each other fast enough. So why does this happen? Well, with the temperature, that is directly related to speed. Okay? The hotter a gas is, the hotter a liquid is, the hotter anything is, the faster its particles move. So that's what we're going to refer to it. Because the particles are moving faster. Now, you could also say that the particles have more energy. That is also accepted because more energetic particles, they move faster. So those two things are exactly linked with each other, okay? You just can't say the particles are hotter, which is what I've seen a couple of times. So what does this mean? Well, it means there's more frequent collisions, and the collisions are more likely to actually result in a reaction. So I don't want to write 2 bullet points because I'm lazy. So here's what I write. So there are more frequent successful collisions. Okay? That's the key point. Which I prefer. I've always written it like that even when I did my GCSEs because it combines 2 points. So sometimes you see more frequent collisions and also they're more likely to be successful collisions. Successful being a reaction happens. I prefer to just write more frequent successful collisions. It's always given. It's all good, okay? You can also say something like more particles are higher than the activation energy, but I prefer this because it makes sense. So let's think about the other ones now. So the other ones are concentration. Well, what is concentration? Well, concentration is simply packing more particles into a smaller area. So let's go back to my analogy of you and your friends walking around a dark room. Now imagine that you have just you and 3 other friends. Okay, you'll probably be able to avoid each other most of the time. But now what about you and everyone in your year group? You're not going to avoid each other, right? So there's more successful collision. Well, sorry, I should say particles are more likely to collide and then have a successful collision. There you go, there's your 3 marks. Okay, what else? Well, what about surface area? Well, again, it's a similar thing. If there's more surface area, you're more likely to collide because there's more space for you to collide on, right? So, for example, the way I explain it is, it's not great for surface area, but if you and your friends are giving each other piggybacks, rather than having 2 separate people, you're more likely to collide as 2 separate people than if you've got each other on your backs, right? And lastly, you have volume. Volume actually decreases the rate of reaction. And again, imagine it. You're in a classroom. There's 30 people. You're kind of likely to bump into each other. But now imagine you're in your massive sports hall. It's less frequent, the collisions, right? It's less likely to hit someone because it's a much bigger area. So you can literally use those kinds of analogies to explain all of these and get all 3 marks every time. Question 2, it's all about crude oil. So crude oil is a resource found in rocks. Most of the compounds in crude oil are hydrocarbons. Complete the sentence. Crude oil is formed by the decomposition of, you can say, it's essentially just biomass. So anything that used to be alive a really, really long time ago. So dinosaurs, plankton, algae, plants, etc. But the idea is that it's just biomass. And again, you can't, a lot of people just say dinosaurs. Not really, because it's not just dinosaurs. There's loads of different species and living organisms that contribute to crude oil. Then it has alkanes are hydrocarbons. So again, those are chemicals that only consist of hydrogen and carbon. Give the name of the alkane molecule that has 3 carbon atoms. So because it's alkane, that ending ANE is going to be the last 3 letters of our word, and the first few letters are going to come from this, from 3. So the prefixes go meth for 1, eth for 2, and prop for 3. So it's prop for, which means 3, and then ane because it's an alkane. And then obviously you have all of your other ones after that. And here we come to our first 6 marker, and it's comparing to alkane molecules. Now I'm going to show you a really easy way to get the full 6 marks on this, and honestly it's basically a spot the difference. It's not that bad, watch. And what we're going to do, it says compare the structure and properties. So what I want you to do first is I want you to write structure and underline it. Okay? And then you're also going to do the same for properties. Okay? Because, and this is, it's kind of a weakness of my strategy, right? I mentioned that if you have 6 marks, you want to put 6 bullet points. I've seen students give 6 structure points or 6 property points, and so you can't get the full marks. You have to give a mixture of both. Now, how many you give doesn't matter. You give 6 in total, so I would suggest 3 structure, 3 properties. However, doing 4 structure, 2 properties is also completely fine. Now, compare the structure and properties. So what does it mean by compare the structure? You look at these 2 chemicals and you say what's different about them. Well, okay. And again, I'm not going to write all of the points. You only need to have 6, right? But I'm going to explain all of them. So point number 1 is methane has 1 carbon atom, hexane has 6. I mean, I'm just looking and just seeing, right? It's not that bad. So methane has 1 carbon atom, hexane has 6. There you go, 1 mark. And guess what we can do now? We can do the same with hydrogen and get the 2nd mark. All I'm doing is reading, basically. So how many do they have? Well, 4 for methane. Methane has 4 hydrogen. Hexane has. And you can either use the formula to work out how many it has, or you can just count them, right? So if you were to count all of these, you should get 14. There you go. 2 marks already. I've almost finished structure. And all I've done is looked at a picture. Not too bad, right? This is like English language now at this point. Now, okay, the next structure one is a bit trickier. However, the easiest thing you can say, the absolute easiest thing you can say, is both are hydrocarbons. So there's a very famous saying that I'm very fond of, which is keep it simple, stupid. Which is, and this is really kind of applicable to maths and science with GCSEs and even A-levels, is, and everyone does this, we have a tendency to overcomplicate things. So far, I've got half the marks, and have I said anything scientific really? I've just looked at a picture and said, well, there's 1 C there, 6 C's there. There's 4 H's there, there's 14 H's there. That's giving me 2 marks. The hydrocarbon thing, okay, sure, that's a bit scientific. But for the most part, it's very simple, right? It's very rudimentary things I'm saying, right? It's nothing groundbreaking. And that's completely fine. So keep it simple, stupid. Now, what are some other things you can say? Well, you can say both, and I'm not going to write it under my structure here, but you could say both have C to H bonds, right? Which, that might even be more rudimentary than what I wrote. I mean, you can literally see that, but knowing that their bonds might be a bit trickier. And you could also say only hexane has carbon-carbon bonds. Right? Nothing wrong with that. So those two are also ones you could do, could kind of use. And yeah, I've got half the marks, and all I've really done is looked at two pictures. Now, the properties is something a bit trickier, but just read this. Right? Technically speaking, you should know that methane will have a lower melting and boiling point than hexane. Because you should know that shorter hydrocarbons are more volatile. They're more likely to be gases. Methane is a gas. Ethane is a liquid, and as you go along, they get into more viscous and thick, sludgy liquids. Okay, so hopefully you should know that the melting and boiling point of a short chain is much lower, so it's much easier to boil it than a longer chain. The reason for that is because each of these lines you see increases the energy. So it means you have to put in more energy to break it apart. Okay? So with this one, it has a lot more energy than this one. Okay? So either way, properties, let's just compare them. Well, first of all, you can say hexane has a higher melting point. Or you could say methane has a lower melting point. Potato, potato. Hexane has lower melting point. Higher melting point. Guess what else I can say? Hexane has a higher boiling point. Or again, vice versa. Now what you can't do is double up. So my next point can't be methane has a lower melting point or methane has a lower boiling point. It's not that rudimentary, okay? So you have to, compare it slightly. So what's the third thing you could say? Well, there's quite a lot that you could say. So for example, you could say that hexane is a liquid at room temperature because if you look at the boiling point, it's quite high. You could say that. You could say that they're both small molecules. You could say that methane is a smaller molecule than hexane. You could say that the forces between hexane are stronger than the forces between methane. Any one of these things. But in my opinion, probably the most obvious is that both are flammable. Okay? Almost all hydrocarbons are flammable. And generally speaking, the smaller ones are more flammable than their bigger ones. Okay? But any of those will do. What else can I think of? Methane is more flammable than hexane. Neither conduct electricity. Hexane's more viscous than methane, so that's what I was talking about with the sludginess. Any one of those is completely fine. But again, basically 6 very short sentences for 6 marks. Pretty nice once you get it nailed down. And for our last bit of kind of hydrocarbons, we have cracking. So cracking literally just means you have your hydrocarbon chains, if we go back up here, and you split it up into multiple smaller hydrocarbons. That's all it means. Okay, you're cracking them apart if you'd like. Now, if we look here, how do I look at a cracked reaction or a cracking reaction? Well, not too bad. All you have to know is that both products are always hydrocarbons. Now, they can be alkanes or alkenes, but they're always hydrocarbons, which means you're just going to have another CH. Now, what do you need to do? Well, it's kind of like algebra. I have 10 C's here and only 2 here. So the rest of the C's must be in this molecule, right? Because remember, you can never lose atoms. They don't vanish. So 10 minus 2 means there must be 8 C's here. Because again, 8 plus 2 gives me 10, so it's all balanced. We have 22 H's here and 4 here, so it means we must have 18 over here. That's it. Okay, so your carbons and hydrogens on the left should equal the carbons and hydrogens on the right. That's it. Now, the test for alkenes, this one might be a bit tricky. All you should know is that the bromine, which is a brown liquid, or orangey brown, however you want to describe it, if there are alkenes, will break the double bond and bind to the hydrocarbons, turning them see-through. So the bromine basically reacts with the alkene. It breaks the double bond, so it bonds with the hydrocarbon, which means there's no more bromine in the water, which means the water goes from a brownish liquid to a clear liquid again because it's water, right? So the test is bromine water. Bromine is normally brown or orange, so when it reacts it turns colourless. So you can say it goes from brown to colourless, or you can just say it turns colourless. Either one's completely fine. So or brown to colourless. Both those are fine. Also, if you say orange, that's also completely accepted, of course. It's the same. Brown and orange are basically the same thing, don't worry about it. For this question we have methods used to produce potable water. Potable literally just means drinking water in this context. Don't ask me why they need to have complex words for everything, but you know. Depend upon available sources of water. And we need to suggest how copper sulfate can be used as a test for the presence of water. Now, this might seem a bit obvious, but you need to say what you do with the copper sulfate. So the first thing is that you're going to add water to the copper sulfate. So add water to, and we tend to call it anhydrous, which just means it isn't wet, there isn't water present. Copper sulfate. And then you're going to describe the change that happens. So copper sulfate, anhydrous copper sulfate specifically, is white. So it changes colour from white. And then when it hydrates, so it stops being anhydrous copper sulfate, it turns to blue, okay? So that's why they specify anhydrous copper sulfate. Anhydrous just means there's no water present in it. The boiling point is used to check the purity of a sample of water, but in chemistry, what is meant by a pure substance? So a pure substance, which you might already be aware of, and you might kind of know the definition, but you don't really know the science kind of terminology. It just means that there is only one element or compound. So it just means one element or compound. So if you have, let's say, water, pure water will just be H2O molecules. That's it. Nothing else in there at all. The other way you can kind of define it is that it's an element or compound not mixed with any other kind of substance. But yeah, in general, the idea is that there's only one molecule or element or atom floating around in there, one type of those things, okay? So this question is one of those kind of maths questions, really, because working this out isn't really a set thing in your spec, but they can expect you to know it. So there is some kind of math skills based in this. So I'm going to take you through it. So the boiling point of a 250 gram sample of water is 100.6 degrees. And again, this is a sample of water, it's not pure water. The boiling point of pure water is 100 degrees. Every 1% of impurity increases the boiling point of water by 0.12 degrees. So calculate the mass of the impurity in the sample of water. So here's the kind of information that I care about. The more impure the substance, the more impurity there is, the higher the boiling point. That's the information I'm thinking of. And it tells me that every 0.12 degrees gives me an extra 1%. So what I should work out is what is the difference in the boiling point. So the difference in the boiling point is just 100.6 minus 100, which is 0.60 degrees Celsius, okay? Now, how many times or how much percent of impurity do we have if it increases by 0.12 each time? There's two ways to do this. You could keep adding 0.12, so do 0.12, 0.24, 0.36, all the way up to 0.60 and just work out how many times that is. But, and hopefully as I explained that you may have thought of something, this is the same as just dividing 0.6 by 0.12. That will give me the percentage. Because again, each 1% increases it by 0.12 degrees Celsius. So 0.12, 0.24, 0.36, all the way up to 0.6 will give me the percentage that I'm looking for. The other way to work that out is to just divide the two numbers. So the percentage impurity is just equal to 0.60 degrees Celsius over 0.12. That's basically just 60 divided by 12, which hopefully you may know from your maths is 5%. So the impurity is 5%. Okay, so far we've actually got 3 marks so far. 2 marks so far. So the last step is to calculate the mass of the impurity in the water sample. So what this impurity is saying is that 5% of this sample is the impurity. So in other words, all I need to do is take 5% of 250 grams. So the impurity, so the mass of impurity, is 5%, and when I say of, I just mean times 250 grams. So I can actually do that on a calculator nice and easily and basically just type the exact same thing in. So 5% button times 250, which gives me 12.5 grams, which is the correct answer. Perfect. This is one of those standard processes that you should hopefully be able to know. So it says, explain how distillation is used to obtain potable water from salty water. So how can I get drinking water from salty water? Now, distillation, just so you're aware, always involves heat. It means, literally, to separate by heat. Okay? So if you think of fractional distillation, what do you apply? Heat, right? You heat up the hydrocarbons and siphon them up to different melting points, right? Boiling points in that case. So again, distillation just means separate by heat. If you know that, you can actually get a couple of marks even if you have no idea what you're talking about. Think about it. I have salty water. So what is that? It's water with salt in it. I know, right? This is why I'm a teacher. It's amazing. So I want to separate water from salt by applying heat. That's basically the 4 marks. You heat up salty water so the water evaporates and the salt is left behind, and then you just cool down the water vapor, which is just liquid water. That's it. 4 marks. Really, really quick and easy. Okay? But to write it in kind of a short form, this is what you'll do. So, you heat up salty water. Water. So that the water evaporates. Water evaporates. You can also add, if you'd like, leaving the salt behind. You don't have to though. So what I'll do is I'll put the tick mark after this. That might just be for your notes, just so you're aware, because keep in mind, understanding in science is really important for getting those marks. It's a lot easier to remember something if you understand it. Otherwise, you might as well just try to be memorizing stuff in like Turkish or something. Then what you do is, now you have this vapor and you have the salt, you need to cool down the vapor again in order to get drinking water. So then you cool down the vapor. Which condenses to form water. And again, you could write this a lot faster than me. My hands are a bit sweaty right now. It's absolutely boiling. But yeah, you could write that pretty quickly. And that's where you get the 4 marks from. Okay? So the reason why this might look weird, because these aren't whole sentences, right? Cool down vapor, condense to form water. The thing is, if you wrote this in full sentences, this is where you're getting the marks from. So you can just write it as a bullet point. It's a lot quicker and a lot easier. Okay? But if you want, you can add a few extra words to make them complete sentences if you'd like. So here we have, obtaining potable water from salty water is a lot more expensive than obtaining potable water from groundwater. We need to explain why. And we need to refer to the processes used in both methods in your answers. So what this means is, because there's 2 processes and 2 marks, I want to do 1 bullet point for the salty water and 1 bullet point from the groundwater. Well, first things first is let's start with the salt water. So why would you think that might be expensive? Well, if we go back to our previous answer, you need to heat up salt water. Now, you might think, okay, that's not too bad if I just want to drink. But imagine if you're trying to provide water for 1 million people. Heating up millions of litres of water is incredibly difficult. Incredibly difficult. It's very expensive. So the reason why is distillation, and you want to refer to the name of the methods, by the way, because otherwise they're not going to be able to tell the difference. So write that distillation requires energy to heat up water. There's energy to heat up water. And that's it for distillation. Now, what about the other method? Well, we're just going to call it groundwater because that's what they've referred to it as. So groundwater. Now, what is the process of getting normal drinking water, potable water from groundwater? Well, all you need to do is essentially get it out of the ground, and that's quite easy. You can do it basically from lakes if you wanted to, or from wells underground, whatever you like. And all you need to do is sterilize it and filter it. Now, hopefully you remember this from your kind of sterilizing water kind of module. To sterilize water is actually really quite cheap and easy. The first thing you do is you filter it. So you literally have a metal grate, okay, so literally just like a metal grate, which, you know, like that, and the water passes through it, and all of like the twigs and like, I don't know, dead animals or whatever happens to be in there get caught up. Then you sterilize it through various ways. Normally, they just pump chemicals into it and then drain the chemicals out. And that's it. You just put a little powder in there and you're done. Okay, it's very, very quick and easy. So groundwater only needs filtering and sterilizing, which is relatively easy and cheap. This question is kind of universal to all three sciences because all we're going to be doing, well, you're going to see in a second. So industries use the Earth's natural copper resource to produce useful products. Here's the world production of copper. Okay, and as you can see, well, all you're going to do is describe the trend, okay? And it's quite simple, really. So it's 2 marks because there are 2 things you need to say. And again, this is universal for maths, biology, chemistry, and physics. So what's the trend? Well, the first in trend is that it's increasing, right? So production is increasing. But that does not give you 2 marks because it's not just increasing, is it? Right? It is increasing, but is it just increasing? Let's think of like how steep the line is. It's getting steeper and steeper and steeper, isn't it? So it's at an increasing rate. That's the key second point here. And again, this is why bullet points are so useful when it comes to writing out your science answers, because 2 marks, I can see that I've got 2 points, so I should get 2 marks. Okay, it's very kind of specific in that sense. But again, just make sure you don't just say it's increasing, you have to say it's increasing at an increasing rate. And for part 2, it says, suggest one reason why. Well, if you think about what's happening in like the world, there's more and more people in it, and we have more and more products that use copper. So simply, increase in demand. You could also say increase in population, as I said originally, but either way, that would be it. You can also say that there's more uses for copper as well, if you'd like, because you use more electronics, which have copper wire inside them. And here's a relatively interesting question. So it says, suggest one reason why this trend can't be used to predict the future. So for example, if I go to the future, why can't I just continue going like this or something along those lines? Well, the reason being, there's a few different reasons you can say, but think about it. When you're mining copper out of the ground, it's a limited resource. So that's one reason. It's a finite resource. And if it runs out, then obviously the production is going to start to nosedive down to 0. So it may run out. But some other things is, well, what about recycling? Right? If we start becoming more and more conscious of recycling, then we won't have to produce more copper. We can just reuse the copper that we've already got. And another thing is also technology, right? We might use a different metal in the future. Because even as human beings, we went from kind of bronze to iron to steel, and now back to kind of copper. So it could be in the future that we use some completely different material that doesn't even exist right now, which means we won't need copper. Any of those answers is completely fine, but I think, in my opinion, the best one to remember, I guess would be the way I would put it, is this finite resource thing. It's the same thing if it's production of oil or production of literally anything. It's a finite resource. If it was production of something that's biological, like wheat or food, then you could always say that we will run out of space. You know, so the idea is that it runs out, everything's finite. So this is quite an interesting topic, in my opinion. So high-grade copper resources are now difficult to find, so they use phytomining. Now, how do you remember what phytomining is. Well, if you think about phi, that's kind of, it reminds me of plants, okay, and photosynthesis and things like that. And simply, it's just mining using plants. And I was going to go through the stages of what exactly happens, but that's literally what this question is asking us to do. We just need to put the correct order here. Now, I'm just going to go through the order here, and then we can just tick the one that kind of makes sense. Now, with phytomining, what exactly happens? Well, the idea is that when you have a plant, so imagine this is like the roots, this is our little, like, sunflower or something. It looks more like a tree. Yeah, fine, a tree. The idea is that its roots will begin to absorb copper into the plant, which the plant doesn't actually use. Okay, so the first step is simply that the plant absorbs metal compounds through their roots. And this happens with a few different metals, but copper is one we're talking about here. Now what happens next is that once the plant grows to adulthood, we then harvest the plant. So what that means, if it was a tree, we would cut it down. If it was some kind of, I don't know, sunflower or whatever, we would cut it down as well. And what we can do is we can actually burn this plant. And what will be left over in the ash is copper compounds, which we can then kind of extract copper metal from. Okay, so in this case, again, as I've said it, copper compounds from ash are extracted, and in this case they're dissolved in acid, and then the solution of copper compound is electrolyzed in order to separate out the copper from the ash or any other liquid that's in there. So in terms of which order it is, it's B, D, C, A, E. So B, D, C, A, E is this one down here. And this, again, is actually quite an interesting question. Normally they ask you for advantages when they have these kinds of methods because they're eco-friendly, so to speak. So they normally ask for advantages, but we now need to think of disadvantages of phytomining. Now, in my opinion, if I imagine it, if I'm thinking about it, let's say it is like a sunflower I've got, and I burn it down, and I'm sifting through ash and using acid to separate it, there really isn't much copper that's going to be found, right? Whereas if I'm mining in underground, I'm getting huge chunks of rock that contain copper. You can actually see copper in the rocks in some cases. So the thing here is that it's a very low yield compared to just, mining them out of the ground. And what else? Well, if you think about how we do it, when we have miners, I mean, it's less so in this case, but they go down with pickaxes and they chop chunks away and then they just chuck it into a smelter and that's about it. It's very quick. Whereas with this method, we have to wait for a plant to grow, right? Which is quite tricky. So it's also slower as well. Slower than traditional mining, that's right. Because I don't like just putting one word sometimes. Okay. Other things that you can say is that you need a huge amount of land. So currently we use most of our land for agriculture, so making food. So then how do we allocate land for phytomining instead? And how do we get that much land? Do we have to cut down a bunch of forests, which is bad for the environment? Things like that. So low yield, it's slower, and you need a large amount of land. Here we come on to a 5-mark calculation, which is somewhat interesting, I suppose. So it says in 1 year, 8.89 times 10 to the 9 kilograms of copper was produced. 41% was recycled copper. The energy needed to produce 1 kilogram of copper from the actual ore is 70.4 megajoules. For recycled is 27.2. Calculate the difference in energy used if all the copper was produced from recycling. Give your answer to 3 significant figures. So it's 5 marks because there's a few different steps. So what I'm going to do is I'm going to say in this year, so let's say currently maybe, we're going to work out how much energy was required to produce this amount of copper. So 41% was from recycled copper. So we can do this in multiple steps or we can do it in one big one. So I'm going to do it in kind of multiple steps. So let's do the recycled first. So first of all, we have 41% of the mass was produced by recycled copper. So 41% of, so we're going to do times 8.89 times 10 to the power of 9. So I'm going to put it in brackets, although you don't technically have to, but let's do it. So we have 41% multiplied by 8.89 times 10 to the power of 9, whoops, wait, close bracket, means that this number here, which again we can just save on our calculator, we don't actually need to write it out, but just to do it for completion's sake, 9 kilograms. So the actual energy required is going to be this amount of energy, 27.2 megajoules, times that massive long number. So times 27.2, which gives me a absolutely enormous amount of energy. So we have 9.91 times 10 to the power of 10 megajoules. Okay, that's a ridiculously large number, by the way. It says give your answer to 3 significant figures, so I'm just going to put everything as 3 sig fig. And that means the rest of it must have been produced kind of using normal mining methods, okay? So if we do, does it say, let's just say normal. Actually no, it says from ore, let's use ore. So that means 41% of 8.89, so we have two options. We can either do 8.89 times 10 to the 9 minus this, or we can just say, well, what's 100% minus 41%? That is 59%. And then multiply it by the exact same number. And we're going to do the exact same thing again. And again, like I did want to point this out, that you can do the whole thing on a calculator if you want. You don't need to really write anything down. I would just write down like things like the energy and everything. But you don't really need to write much down. So that's why it's taking me a fair amount of time to do this. Whereas in reality, you do it a lot faster. So for example, after I got this amount, I would then just times it by 70.4. But just for your sake, I'm writing it all out just so you can kind of compare notes. Therefore, energy equals, what was it, 70.4 times that number. So now times 70.4 gives me 3.69 again to 3 sig fig. So then in total, all we're going to do is add this number and this number for the total energy, okay? So add on 9.91 multiplied by 10 to the power of 10. Whoopsies. There we are. Which gives me 4.68 times 10 to the 11. Now, if the whole thing was just recycled, what would we do? Well, all we need to do is times this mass by 27.2. So let's do that right now. So the mass was 8.89 times 10 to the power of 9. And we're multiplying that by just the recycled energy. Ooh, that was close. And that gives me 2.42 times 10 to the 11 megajoules. So the difference is just, you can actually just subtract the numbers in front, by the way. You can just do 4.68 minus 2.42 and then put it as times 10 to the 11. But all you're doing is subtracting those two numbers. So 4.68 multiplied by 10 to the power of 11 minus the answer gives me 2.26 times 10 to the power of 11 megajoules. And that's it. So for 5 marks, it's not too bad. And again, you could kind of do this a lot faster if you just used it on your calculator instead of kind of rounding all the numbers and writing them all out. So hopefully that isn't too bad. This question is all about pollution. So atmospheric pollution is emitted by cars, and some of this pollution is called nitrogen dioxide. And all we have to do is describe how nitrogen dioxide is produced in the engine of a car that burns fossil fuels. So this is quite an interesting question because the actual process is relatively simple. So you don't need to remember that much. So if we have a look at this compound, it has nitrogen and oxygen, right? So we can get quite a few of the marks just by saying this. Nitrogen reacts with oxygen. That's 2 marks. So if you'd like, we can say nitrogen reacts with oxygen to produce nitrogen dioxide, so to produce NO2. But technically speaking, you only need that and that. Okay, so the idea here is that there's nitrogen just in kind of car engines naturally, either from the atmosphere or whatever, and oxygen's obviously in the engine because it's burning stuff, so there has to be oxygen there. And the idea is that these will react in order to produce NO2. Now you might be thinking, well, why doesn't it produce NO2 just in the atmosphere? And here's the key thing. What's the difference between an engine and the atmosphere? Well, the engine is, basically on fire, right? There's a constant explosion going off, which means it's very hot. So the key part here for the 3rd mark is at high temperatures. So you can literally just write at high temperatures, nitrogen reacts with oxygen. That's it. That's 3 marks. Okay? Really kind of clean and easy question there once you know the process. And again, 2/3 of the marks are just gotten from reading the chemical formula. For this next question, we have a table showing the concentration of nitrogen dioxide in the air at 3 different areas in week 1. So we have a city centre, countryside and motorway, and these are the kind of values for every day during the week. And you can kind of have a glance at the information, but you don't need to really study it that much, okay? And then we're going to look at part 2, and that's when we're going to then go back and actually have a look at the information. It says the mean value for the nitrogen dioxide in the air for the whole week is in the city centre, so that's a kind of key point that we want to highlight, is 33 micrograms per cubic metre. And we need to work out the value of X for the concentration of nitrogen dioxide in the air in the city centre on Sunday. Okay, so I'm just going to write up the 33 over here. Now, if you look, the X, okay, that makes sense that, we know we're probably going to have a question asking us to find out that value, and that's exactly what this question is. And it's saying that the mean for the city centre, so for all of these values in the middle here, well, not in the middle, on the left, have a mean of 33. Now, how do you work out the mean? Well, what you do is you add up all of these values and divide by the number you have. So what we're going to do is we're going to literally add up all of these values. And I'm going to write it out. Actually, we can do it in a bit of a simpler way. If we add up all of these other values, so we have 35 plus 30, plus 37 plus 37 plus 34 plus 37 plus 29, we have 209 plus X, because we don't know what X is, and what would we be dividing by? How many numbers do we have? We have 1, 2, 3, 4, 5, 6, 7. So over 7 should equal 33. So now it's just simple maths, right? Well, not simple, but it's maths. Times both sides by 7, you get 209 plus X is equal to 33 times 7. So 33 multiplied by 7, 231. And then minus 209 from both sides, and you get X is equal to 231 minus 209 gives us an answer of 22, and that is the correct answer. Okay, so again, a little bit of maths, but hopefully not too bad. Now for part 3, this is a bit of kind of experimental data, so if any of you are interested in doing experiments in the future, in terms of kind of university and as a job, uncertainty is going to be your bread and butter, okay? It's going to be something you're going to deal with all the time. So hopefully this hasn't put you off of a career in experimental science. But each value in table 3 has an uncertainty of plus or minus 2 micrograms per cubic meter. Explain why it's most significant for the countryside data. Now I'm going to hack this a bit for you again, because again we can kind of cheat, because they've given us the answer. It's most significant for the countryside data. So I'm going to explain this scientifically after I've explained the hack. Okay, so we're going to cheat, and then I'm going to tell you exactly what it means scientifically. So remember this plus or minus 2, right? But remember this sentence. For the hack, we just care about this sentence. Most significant for countryside data. Why? And we have to explain. Okay, so 2 marks, so we're going to have 2 bullet points. So, if we have a look at the countryside data, what do you notice about it immediately compared to the other 2 pieces of data? Well, the thing I notice about it is it's only 1 digit. which means it's a lot smaller. So now this is like, it's causing me to think, well, the fact that it's smaller must be the reason why it's most significant for the countryside data, right? That's why the uncertainty is the most significant for countryside, because the data is much smaller. That is actually your first mark. Okay, and I haven't used any science, right? I've just used kind of pattern recognition. So the countryside has the smallest set of values. Has the smallest values. Okay, now here's where it's going to be harder to hack, right? But 1 mark out of 2, if you don't know anything about uncertainty, that's better than 0 out of 2, right? It's infinitely better. So now we need to think about why this would affect it. Well, what is uncertainty? So now I'm going to go into the kind of scientific description of it, okay? What is uncertainty? Well, what it is, I mean, what does it mean when you're uncertain of something? It means you're not sure. So if I said, what's your percentage, what's your average grade, or your average mark in your maths test, you'd probably say about 65 or about 70. You wouldn't give me a definitive answer, would you? If I said, what have you gotten on your papers on average? You wouldn't say, oh, exactly 53.4 or something, right? Because you don't know. You're taking an educated guess. That's basically what uncertainty is. Okay, we're saying that each of these values are correct, give or take 2, right? So give or take 2. So I'm saying that this could be 37 at max, 33 at minimum. Okay? So in the way this could work in your kind of test is, let's say you get like 50 and then 56, 53, 57. You might say, oh, I get, 55 plus or minus 2. Like 55, give or take 2 marks, that's my average. That's what uncertainty is. Now, here's a kind of an estimate for you. What's better? If I said that there are 1 million people I've lost count of how many zeros I have. 1 million people in my city, give or take 2 people. Or if I say there are 10 people in my class, give or take 2 people. Which one's like more impressive? Which one's more significant? Well, this, right? 10 plus or minus 2, that's a big difference, right? The difference between 12 and 8, that's pretty big. But the difference between 1 million, so the difference between 999,998 and 1 million and 2, that's not that much, right? And again, think of it in terms of money. If I was going to say, I'm going to give you £1 million, give or take £2, right? Like, maybe I only end up giving you 999,998. Would you care that much? Whereas if I owe you £10 and I only give you £8, that's a pretty big difference, right? So that's what uncertainty is. So the reason why uncertainty matters more for smaller values is that it's a bigger proportion or percentage of the value, right? And again, so the uncertainty, which is 2, is a bigger proportion / percentage of the value. Okay, and that's kind of the idea we're looking at. I should say of the value, actually, not a full stop there. And that's the overall idea. So I hope that makes a bit more sense, right? And again, uncertainty just kind of related to real-world allegories, which is basically all I do with science. I just relate it to some other analogy that I have, and it tends to get me the right answer. For the next part, we have nitrogen dioxide is removed from car emissions by catalytic converters, probably one of the best inventions in recent history. In the 70s, all cars were mandated to have them to reduce pollution dramatically. Really, really important. But anyways, enough about the nerd stuff. In a catalytic converter, nitrogen dioxide reacts to produce nitrogen and oxygen. Complete the equation for the reaction. You need to balance it as well. How fun. So, how would I approach this? Well, the way I would approach this is, I would first say, okay, it produces nitrogen and oxygen. So I'm going to put N and O. That doesn't give me any marks yet. But in a lot of cases it would. But there's a reason why this doesn't give me marks just yet. Have you ever seen an N or an O by itself? They are diatomic, which means they only exist in pairs. That is 1 mark. I haven't even balanced it, but that is 1 mark. Okay? So again, there's not really much of a way to remember this, but hopefully with practice, nitrogen and oxygen, they always exist as pairs. They have to exist. They're diatomic molecules, okay, which means they always exist as pairs. It's very rare to get oxygen by itself. It doesn't like to be by itself. It likes to pair up or triple up in terms of ozone. Same with nitrogen. So now we need to actually balance it. So if I have how do I balance equations? That's a really good question. Now, in the exam, I would write these underneath, right? So I'd write out the equation and write it out. But because I have the magic of computers, I can write in my values and then change them. So if I have a look here, all I do is I go through step by step and I say which one's correct. So how many nitrogens do I have on this side? I have 1. And how many do I have on this side? I have 2. So I need to fix that. How can I fix that? How do I make 1 into 2? I put a 2 in front. Okay? Now, my nitrogens are nice and balanced because I have 2 nitrogens on the left and I have 2 nitrogens on the right. So now let's go on to our oxygens. How many oxygens do I have? And this is where people always mess up. There's O2 and then 2, which means in total it's 2 times 2, 4. Okay, the way you can think of it is if you cover up this here, we have, in this case, 2 oxygens, right? But then when I add the 2 in front, I have 2 lots of that molecule. And that molecule has 2 oxygens. So 2 times 2 is 4. Now how many do I have on the the right hand side? I have 2. Well, that doesn't balance yet. How can I make 2 into 4? I can shove a 2 in front, and now they're balanced. Okay, because now I'll have 4 in front. And that is the balanced equation. So 2NO2, N2, 2O2. Okay? So again, that's after when this becomes kind of, this one becomes 2, and this one becomes 4. Nice and, well, not easy, but it's okay when you go through it. And again, just go through systematically. Match all the N's, match all the O's, and any other letter as well. It says here, the catalyst in a catalytic converter contains platinum, but platinum is a finite resource. But what does it mean? Well, finite is the opposite of infinite. Infinite means never ending. Finite means ending. So basically, it's a resource that will run out. Cool. And here we have carbon dioxide. Of course, we can't talk about greenhouse gases without mentioning carbon dioxide, probably the most famous greenhouse gas in the world. But emissions from cars contain carbon dioxide. Explain why carbon dioxide emissions during use and operation are not the total carbon footprint of a car. Refer to the stages of the life cycle assessment of a car in your answer. This is a bit misleading in my opinion. I would kind of ignore this partially. But if we look here, what is total carbon footprint? The total carbon footprint for anything or any person or anything at all is just the amount of carbon dioxide that is expelled in everything, in production, in use, in operation. And I've kind of given you one of the marks here. Because A, carbon dioxide is released in manufacturing. Right? In creating the car, we have to use CO2. We have to expel CO2 because we do things like welding, right? Welding bits together. We refine materials, and all of the machines that make a car run on electricity, which is produced by power stations which produce CO2. Okay? Not just that, but CO2 is also released, and this one I think might be a bit hard for people to realise, but it's released in extracting or processing raw materials. So think about it. What is a car made of? Well, I know a lot of them may be carbon fibre, but let's say metal. Metal needs to be mined out of the ground. That produces carbon dioxide. The leather for the interiors, that produces carbon dioxide because you need tanneries, right, to turn cowhide or whatever leather or faux leather that they use. And, you know, you have different kind of materials. You have like varnish and wood, etc. All of those produce CO2 when you extract them. And lastly, but certainly not least, the end of a life cycle. So when they mention life cycle, the reason why I say it's kinda misleading is because life cycle assessment is not really the way I would word it. I would just say life cycle, right? So think about it. Right here, that's when the car's alive, so to speak, right? That's when it's being used. But what about when it's being created, so manufacturing and extracting resources? And what about the end of its life? What happens when a car dies? How do we get rid of it? Well, we put it into like trash compactors or recyclers or anything like this, which produce CO2. So you can just say disposal. Disposal at the end of the car's life cycle. So hopefully that makes sense for kind of this kind of question. This question, we're all talking about ammonia. How very exciting. It's produced when a mixture of nitrogen and hydrogen reacts. So nitrogen, so again diatomic, hydrogen diatomic as well, react in a reversible reaction. That's what this symbol here means, to produce two molecules of ammonia. Now nitrogen is obtained from the air, and the mixture of nitrogen and hydrogen must not contain carbon dioxide and oxygen. So explain how a sample can be tested to show that carbon dioxide is not present in the mixture. So basically we're testing carbon dioxide, and there are basically two ways. So all you're going to do is have lime water, or, so you don't need to do both, I'm going to put a slash, calcium hydroxide solution. And what happens when it's in the presence of carbon dioxide? Well, when it's not in the presence of carbon dioxide, well, again, because we're testing if it's not present, not if it is present. So if it is present, it turns milky or cloudy. But keep in mind, we're trying to test if it's not present. So in this case, it should stay colorless. And that's it. Okay, because you're right. Here they were trying to trick you, because obviously lime water calcium hydroxide solution, the pathway in your brain that's probably firing is that it goes cloudy with carbon dioxide. But again, we're testing if it's not present. Catalyst is used in the reaction. Explain how a catalyst increases the rate of reaction. So I'm going to just kind of give you the answer. So first of all, catalysts reduce the activation energy. And how do they do that? They provide an alternate pathway or alternate reaction. Okay, so provides alternate pathway at a lower activation energy. So how does this, and now in terms of the actual science, what I'm going to do is quickly explain it. Essentially what they do is they provide an intermediate reaction. So basically the reactants will react with the catalyst and then react again to form the products. So if you'd like, it's like they react to form something else. So it could be whatever compound, and then they react again to form ammonia. And the idea is that it takes less energy to go this way than it does to go straight from left to right. Okay, so that's basically how a catalyst works. Now we're talking about how equilibrium is reached. So again, remember this is a reversible reaction. So it essentially means that as these react, they form ammonia, and ammonia will then break back down into nitrogen and hydrogen, but obviously at a certain equilibrium point. So how is an equilibrium reached? Well, the first thing that you need to write is in a closed system, because you can't actually have an equilibrium without a closed system, because otherwise gas will just continuously leak out. Okay? And in a closed system, what does it mean? It means that the forward and reverse reactions occur at the same rate. So forward and reverse reactions occur at the same rate. And that's the key thing, is that it doesn't stop. You know, the reaction never actually stops. It's just that because they're reacting at the exact same rate, you can't notice any differences. Okay, but that's the key point there. So they still occur, it's just that they occur at the same rate. The next bit suggests how the catalyst affects the equilibrium position. And this is actually a really common mistake, because you might think that it shifts the equilibrium position so that you're actually getting more product, which is a good thing. But the catalyst doesn't do that. What it does do is it increases the rate of reaction, but it increases the rate of the forward and the reverse reaction by the exact same rate, which means they cancel out. Okay? Because again, the main reason we use catalysts is actually to lower activation energy, because it becomes cheaper to run the actual experiment. If, let's say, without a catalyst I need 1000 degrees Celsius, but with a catalyst I need 600 degrees Celsius, that saves me a lot of money in terms of heating up the experiment, rather than actually getting more product out. So here's the 2 marks. Equilibrium stays the same or is unaffected. So it stays the same or unaffected. And the reason for that, so again, keep in mind, this is the actual suggestion. If it's affected, so if it's, you know, affected or unaffected. And now the reason is because the forward and reverse rate of reaction are increased by the same amount, which effectively means it doesn't change that at all. Okay. Here it's mainly kind of a memory kind of game where you have to just remember about the process of ammonia, which is a process you're supposed to know. What is the effect of increasing the pressure on the reaction to produce ammonia? Well, I can explain it in a slightly different way. So first of all, you should just know that it increases. But second of all, think of it this way. To increase the pressure requires money, right? You have to actually put energy into the system to increase the pressure. So why would a company or a factory do that unless it increased the yield? Right? Why would they just throw money away by increasing the pressure when it gives them no benefit? And again, the benefit in this case is that you want to produce ammonia. That's the whole goal, right? It's like if I said to you, okay, read this book, but it won't improve your grade in your exam. Why would you ever read it? However, if I said read this book and your grade will guaranteed go up by at least 1, then you have a reason to do it, which means you would do it. Well, hopefully anyway. That's the same kind of thought process that companies make. Here is a bit of a tricky question to kind of conceptualize. So the forward reaction is exothermic. So just as a reminder of what the forward reaction is, that's producing ammonia is exothermic. So we release energy. And here it says, explain the effect of increasing the temperature on the yield of ammonia gas produced at equilibrium. So again, we're talking about the actual yield of ammonia. So the yield of the forward reaction. So, and again, it does say produced at equilibrium. Now, the equilibrium bit is really important, okay? Because again, we have the forward and backwards reactions. Here's the key thing. With a reversible reaction, one of them is always exothermic and the other is always endothermic. Okay, that's a key thing. So if that way is exothermic, then this way, i.e. the breakdown of ammonia gas, is endothermic. Now what does that actually mean? Well, endothermic means it takes energy in. Okay? Whereas exo means it puts out energy. And again, remember with chemistry, one of the kind of key things is that energy and temperature are basically the same thing. The more energy a system has, the hotter it is. And the hotter a system, the more energy it has. They're essentially interchangeable terms. So let's think about this now. If we put more energy into the system, which reaction will take place faster? Will it be the one that puts out energy or the one that takes energy in? Imagine it this way, right? If you go to a shop and you're going to buy as much sweets as possible, would increasing the amount of money you have make you want to buy more sweets? It would, right? Because you have more energy, you have more stuff to deal with. So if we increase the temperature, we increase the energy, endothermic reactions take place faster because there's more energy for them to use for reactions. Okay? Because again, endothermic requires energy. Without energy, endothermic reactions just won't take place at all. So I hope that makes a bit sense. So the breakdown of ammonia gas will speed up, which means the yield will decrease because you have less gas. It's breaking down faster. I hope that makes sense. So the yield decreases because the rate of endothermic reaction increases. I'm hoping that makes some amount of sense. I hope I've explained it in maybe a slightly different way which you find useful or helpful. I hope so anyway. But if you do have any questions, your exam is in a few days depending on when this video actually uploads, because YouTube's still being a bit wonky in terms of the uploads. Feel free to comment, feel free to message in the Discord, feel free to email me and I'll get back to you as soon as humanly possible. with any questions that you may have. But I hope you find this useful. Best of luck in your revision. You've got one more week of exams, maybe the Monday as well afterwards, or the Wednesday if you're doing further maths. But let's just get through to the end.